Hello everyone, welcome to my channel Physics for Engineers. I am Dr. Thirumalrao Gurugubelli, working as Associate Professor and Head, Department of Basic Sciences, School of Sciences and Humanities, SR University, Warangal, Telangana, India. Before we begin, let us understand why physics is important for engineers. Today, almost every technology around us, including smartphones, laptops, LEDs, solar cells, fiber optic communication systems, medical imaging devices, and semiconductor chips, is based on the concepts developed through the modern physics. The classical physics developed by scientists such as Newton's, Maxwell, Faraday successfully explained many new natural phenomena. However, scientists started investigating atoms, electrons, and light at microscopic scale. They discovered several observations that classical theories could not explain properly. This led to the birth of modern physics in the early of 20th century. The modern physics mainly consists of two revolutionary theories. One is quantum mechanics and relativity. These theories transformed our understanding of matter, energy, space, and time. In this course, we will explore the fascinating world of atoms, electrons, semiconductors, quantum phenomena, and advanced technologies that from the backbone of modern engineering. By the end of this, we will understand how discoveries in physics have enabled the development of electronic devices, communication systems, and modern computing technologies. Let us begin our journey by the first understanding what is physics, why physics actually means, and how the modern physics emerged from the limitations of classical physics. What is physics? Physics is often called the fundamental science because it seeks to understand the laws governing the universe. Traditionally, physics can be divided into two broad categories. One is classical physics and modern physics. The classical physics refers to the branch of physics developed before 1900. It includes topics such as mechanics, thermodynamics, electromagnetism, optics, and acoustics. The classical physics successfully explains the motion of planets, operation of missions, heat transfer, and electrical circuits. For example, when we calculate the trajectory of a cricket ball, design a bridge, or analyze the motion of a vehicle, we are applying classical physics. However, towards the end of the 19th century, scientists encountered several experimental observations that could not be explained by the classical theories. Examples including black body radiation. The classical physics was failed to explain the black body radiation. The photoelectric effect, atomic spectra, and the stability of an atom. These concepts were not explained by the classical physics. So these failures leads the scientists to develop the entirely new concepts. As a result, the modern physics emerged. The modern physics primarily deals with the quantum physics, atomic structure, nuclear physics, special theory of relativity. Unlike the classical physics, the modern physics studies phenomena occurring at extremely small scale, such as atomic or subatomic particles, or at extremely high speed approaching the speed of light. Think about your smartphone. The processor chip, memory device, sensors, laser communication systems, and display technologies all depends on the principles of modern physics. Therefore, the modern physics is not just the theoretical object, it directly influences the technologies that engineers design and use every day. In the coming theories, we will see how the limitations of classical physics paved the way for the revolution of discoveries. The modern physics did not emerge from the work of a single scientist. It is built through the contribution of several extraordinary researchers whose discoveries completely changed our understanding of nature. One of the most influencing scientists was Albert Einstein. Einstein introduced the theory of relativity, which revolutionized our understanding of space, time, mass, and energy. The famous equation E is equal to mc square that changed the uh, ideology of many scientists. Another key figure was Max Planck. He proposed that the energy is emitted in discrete packets called quanta or wave packets. This idea laid the foundation of quantum mechanics. Niels Bohr developed a new model of atom and explained the atomic spectra. Werner Heisenberg introduced the uncertainty principle, showing that certain physics quantities cannot be measured simultaneously with absolute precise. Schrodinger developed the wave mechanics and the famous Schrodinger equation. That Schrodinger equation turns the shape of the physics. The scientists challenged existing belief and they proposed entirely new ways of understanding the nature. Before their discoveries, scientists believed that matter and energy behaved predictably. Modern physics revealed that the microscopic world behaves very differently. That means the behavior of the material is different at macroscopic level and microscopic level. Example, we can see the nanomaterials. The nanomaterials properties are completely different at nanoscale when compared with their bulk counterparts. This is exactly how the behavior of the materials are completely changed from uh, the bulk state to the atomic level. The work of these pioneer evolutionary leads to the development of semiconductors, lasers, nuclear energy, medical imaging systems, quantum computing, and many other technologies. As engineering students, it is important to appreciate how fundamental scientific discoveries can evolutively transform society and creates entirely new industries. Early 20th century witnessed one of the greatest revolution in scientific history. Two groundbreaking theories emerged in the early 19th century. Those are relativity and quantum mechanics. The theory of relativity fundamentally changed our understanding of space and time. Before Einstein, scientists believed that time followed uniformly for everyone. Einstein showed that time cannot actually slow down depending on speed and gravitation effects. A practical example in GPS navigation. Satellites orbiting Earth experience different time rates than the clock on the Earth. Engineers must correct for relativistic effects to ensure accurate positioning. Coming to the quantum mechanics transformed our understanding of matter and energy. The classical physics viewed particles and waves as completely different entities. The quantum mechanics revealed that particles can behave like waves and waves can behave like particles. This wave particle dualism, explained by de Broglie, that changes the shape of the modern physics. This strange behavior explains how transistors, lasers, LEDs, and semiconductor devices operates. Without quantum mechanics, modern electronic world not existing. Today, every computer chip contains billions of transistors operating according to the quantum mechanical principles. Thus, the scientific revolution of the early 90s is not just the academic topic. It forms the foundation of nearly every advanced technology used in the world nowadays. What is quantum mechanics? Why it is important? The quantum mechanics world is very different. It is one of the most successful and fascinating theories in science. The quantum world behaves very differently from our everyday experience. One of the fundamental concept is that energy is quantized. This means the energy cannot take arbitrary values. Instead, it exists in discrete packets called quantum, or we can say wave packets, h nu. Imagine climbing a staircase. You can stand only on specific steps, not between them. Similarly, electrons inside the atom can occupy only certain energy levels. Another remarkable property is wave-particle duality. Light behaves both as wave and as particle. Similarly, electrons, which have normally considered particles, can also behave like waves. This wave nature of electrons is exploited in electron microscopes that provides extremely high resolution images of materials. So with this basis, the modern microscopic techniques like scanning electron microscopy and transmission electron microscopy, formerly known as SEM and TEM, they are working. The quantum mechanics also introduced probability. In classical physics, if we know the initial conditions exactly, we can predict the future events precisely. But in quantum mechanics, we can only calculate the probabilities. For example, we can predict the probability of finding an electron in a certain region around the nucleus, but not its exact location. Although these concepts seems strange, they accurately explain experimental observations. The modern technologies based on quantum mechanics included semiconductor devices, transistors, LEDs, solar cells, lasers, MRI scanners, quantum computers. Therefore, quantum mechanics is not merely a theory. It is a foundation of modern technologies civilization. To understand why quantum mechanics was developed, we need to look back at the last 19th century. At the time, scientists believed classical physics had explained almost everything. James Clerk Maxwell successfully unified electricity and magnetism through Maxwell's equations. These equations accurately described the electromagnetic waves and predicted the existence of radio waves. However, several experiments produced results that classical physics could not explain. So, one major problem was black body radiation. The classical theory predicted that a hot object should emit infinite energy at short wavelengths, which was clearly impossible. Another puzzle was the photoelectric effect. Scientists observed that electron was emitted from metal surface when light struck them. Classical theory could not explain why electron emits. That electron emission depends on the frequency of light rather than its intensity. We can see that the emission of the light is not depends on the intensity. It is depends on the wavelength of the radiation. To solve these problems, Max Planck proposed that energy is emitted in discrete packets called quanta. Einstein explained and extended his idea and suggested that light itself consists of particles called photons. These revolutionary ideas became the foundation of quantum mechanics. Thus, quantum mechanics was born not because of scientists wanted a new theory, but because of the experimental evidences demanded it. Here, we can explore the highlights of two critical experiments that triggered the development of quantum physics. The first is black body radiation. A black body is an ideal object that absorbs all incoming radiations and emits energy depending on its temperature. Classical physics predicted that the emitted energy should become infinite at shorter wavelengths. This prediction was called the ultraviolet burst. However, experiments showed that the emitted energy follows a specific distribution and does not become infinite. Max Planck solved this phenomenon by proposing that energy is emitted in discrete packets called quanta. The second experiment is the photoelectric effect. When light falls on certain metal surfaces, electrons are emitted. The scientists expected brighter light to eject more energetic electrons. Surprisingly, experiments showed that the electrons emission depends primarily on the frequency of the light, not on the intensity. Below a certain frequency, no electron was emitted, regardless of the light intensity. Einstein explained This because of the electron emission depends on the frequency. So he proposed that light consists of photons. Each photon carries energy proportional to its frequency. Only photons with sufficient energy can remove electrons from the metal surface. Then those electrons will be emitted from the metal surface. This explanation earned Einstein the Nobel Prize and provided strong evidence for the particle nature of light. Together, black body radiation and the photoelectric effect that demanded the classical physics was incomplete and paved the way for the development of quantum mechanics. That's how the quantum mechanics was developed. This is the basic foundation for the development of quantum mechanics. So these discoveries evolutionarily enabled the modern technologies such as solar cells, photodetectors, CCD cameras, optical sensors, and advanced electronic devices. So here there are several devices you can see, the transistors, LEDs, chips, switches, laser diodes, different kinds of diodes you can see here. These are all developed by the semiconductors. So in the upcoming slides, we will be discussing about the type of materials, the classification of semiconductors particularly we will discuss, and properties of semiconductors, and classification of semiconductors like intrinsic and extrinsic, and the applications of these semiconductor materials like PN junction diodes, VI characteristics, applications of diodes like switch, rectifiers, half wave rectifier, full wave rectifier, bridge rectifiers. All these we'll discuss in the next video. Apart from that, we will also discuss the different types of diodes, Zener diode and its VI characteristics, transistors like BJTs, we will discuss in the next video. Thank you very much for your kind attention, and I welcome you once again for my channel Physics for Engineers. This is the exciting learning journey for the engineering students. Thank you once again.